Welcome back, statistics students. Today I'm going to be going over lab assignment 2. I'm going to be going over the lab assignment 2 template because remember, all of the labs have the lab assignment problems that you're supposed to actually do, fresh, new numbers, new examples that prepare you for the calculation portion of the exam. Not the entire exam, but the calculation portion of the exam. And for every single lab, I provide a lab template, which has different numbers and different examples, but walks you through the exact steps that you'll need to do in order to get full credit on the lab, as well as get full credit on the calculation portion of the exam. And lab assignment 2, the problems in it, essentially, conceptually, are combining our understandings of probability with our understanding of z-scores. Puts them together, our understanding of z-scores, our understanding of the standard normal distribution, which is a bell-shaped curve where you've standardized, right? Go back to that z-score lecture, as well as our understandings of probability, figuring out probabilities. And so this lab is all about practicing that. The first problem has you practice probabilities, where you can count up the various outcomes. The second problem has you just practice z-scores. And then the third problem teaches you a brand new tool, Table A1 in the back of the book, which allows you, if you, number one, know that a variable is normally distributed, and number two, have turned all the scores into z-scores, it allows you to figure out the probability of being between any two particular scores or above or below any particular score. So it's a pretty powerful tool. Kind of like let's take IQ as an example. And let's say I'm a researcher and I'm trying to research only a certain subset of people, like people who have IQs between 120 and 135. Or only people who have IQs between 86 and 101, right? I can use the standard normal table to first turn IQ scores into z-scores, and because I know IQ is normally distributed, I can ask those very specific questions. And so you can see how a question like that combines our knowledge of z-scores, our knowledge of the standard normal distribution, and our knowledge of probability, putting those together to use this tool called a standard normal table. In your book, it's labeled Table A1, in order to figure out a basic probabilities. So let's do that. So problem 1 is just a basic, these are foundational probability problem. Let's say I give you a bag of Starbursts. There's 12 red ones, 14 yellow ones, 13 pink, and 11 orange. And I want to know the probability on, I'm about to reach my hand in and grab a Starburst. I want to know the probability of a pink or a red one. This is an or question. And you may remember from our discussion of probability that as long as events are mutually exclusive, where if one event happens, the other event can't happen. And so what are events again? Well, that's an outcome of me reaching into the bag and pulling out a Starburst. Could be a red one, could be a yellow, could be a pink, could be an orange, whatever color it is an event. And when I ask an or question, I'm opening up the possibilities. I'm saying, what is the probability of pink or red? And here are the formal symbols for that. What is the probability of pink or red? That's the formal symbols, right? P for probability and a little U to stand for one or the other. And because these are mutually exclusive, if you pull out a pink one, that excludes the idea that you could be pulling out a red one at the same time, right? Because you're only going to pull out one, and if it's pink, it's not red. Because they're mutually exclusive, you can just add the probabilities together, which is what I've done here in steps 2 through 4. I've taken 13 and 12, because that's the number of pinks and reds, added them together, and then divided by the total number of M&Ms, which was 50. So 25 over 50 is 0.5. And so the probability of pink or red is 0.5. That's the additive rule. And so I remember it as when somebody asks an or question, what's the probability of one or the other? There's a darn good chance I'm going to be using the additive rule and just adding them together, and I just have to make sure that the events are mutually exclusive. If one happens, the other cannot. In the second part of question 1, I'm asking a different type of question. what is the probability that the first starburst we choose will be yellow? And then on the second trial, I choose an orange one. So this is a very different kind of question. I'm not asking what's the probability of one or the other on one time I pull out a starburst from the bag, but rather I'm suggesting that I'm going to be doing two trials now. And first I fish out a yellow one in my first trial, and then on the second trial I pull out an orange one. So first yellow and then orange, that very specific set of events, right? I'm not opening up my possibilities, but I'm actually narrowing down. I'm saying I only want to know the probability of this very specific set of events. Not yellow then yellow, not yellow then red, not red then orange, but first yellow and then specifically, and then orange specifically. Assuming these events are independent, I can use the multiplicative rule of probability. And so the way I remember, which is what I do here, the multiplicative rule says that as long as events are independent, and they are, right? Think about independence as this way. Does what happened on the first one have any bearing on what happens in the second trial? Well, no, as long as I put the first starburst back, right? That's the sampling with replacement. And so first I take the probability of the yellow one, which is 14 over 50, because there's 50 starbursts, to get 0.28. That's the general probability of just pulling out a yellow one. And then I figure out the probability of an orange one, 11 over 50. And now I get 0.22. That's the probability of pulling out an orange one. And because these are independent events, I can just multiply the probabilities together to get what's called the joint probability of them both occurring. First a yellow one and then an orange one. And as long as they're independent, that will be the correct probability, or 0.06. And remember, probabilities are proportions. So they're always decimals that range from 0 to 1. Always. You never leave it in the fraction format because that would be the ratio, not the proportion. It's the decimal ranging from 0 to 1 that is the proportion. And remember, proportions are probabilities, right? Proportions are probabilities. Now, question 2 is a z-score question. And in this question, essentially, you're going to be practicing calculating z-scores. And then you're going to be demonstrating that rule that I taught you, that z-scores will always have an average of 0 and a standard deviation of 1. And so here's the question. I'm tracking the academic success of 5 students in a kindergarten class. Below are their scores on a standardized reading assessment: 39, 43, 45, 47, and 51. And my first question is, what's the average of these raw scores? Because these are raw scores, right? Is 47 good? I don't know. Is 51 good? I don't know, right? You probably don't know much about a standardized reading assessment. So we're going to first calculate the average: 39, 43, 45, 47, and 51, right? To get a sum of 225, divide by 5, get the average of 45. Now, why did I use the mu symbol? Well, that's because I told you that these were the 5 kids I was tracking. So this is my entire population of scores. So then in this slide, in this question, I ask, what is the standard deviation of this population? And here I've written on there for you. I've written on there the equation for the population. The population standard deviation, right? So I'm telling you this is a population. First, I'm going to take all the scores and subtract the average that I just calculated. Then I'm going to square all those deviation scores. Then I'm going to add them up to get the sum of squares. And then I'm going to divide by n. Why n? Because I told you this is a population, right? And then as a last step, I'm going to take the square root. So that is to refresh your memory on how to get a standard deviation, right? Take each score, subtract the average, square those deviation scores, add them up, divide by n, take the square root. Right? Right. All right, so let's do that. So here we've got the person with the raw score 39. And first in order to calculate the standard deviation, I'm going to subtract the average of 45 to get the deviation score of negative 0.6. Or excuse me, negative 6. I'm going to do that for all the scores. And as a second step, I'm going to square those deviation scores to get 36, 4, 0, 4, and 6 at 36. Then as a third step, I'm going to add all those square deviation scores up to get 80. That is my sum of squares. Then I'm going to divide by 5. Why 5 and not 4? Because I'm dividing by n because this is a population. And then as a last step, I take the square root to get 4. So the standard deviation for these scores is 4. The average is 45 with a standard deviation of 4 points. And notice that I'm showing every single individual tedious step. That's the idea here. Now, on this slide, I'm telling you to calculate and convert all of these raw scores into z-scores. And so let's take this person here with a score of 39 that I've highlighted in yellow. The first thing I'm going to do is subtract the average again to get negative 6. But now I'm going to divide by 4. And so what this is doing now is instead of calculating one number that's for everybody, like calculating the standard deviation of 4, rather I'm taking each and every single person's score, their raw score, 39, 43, 45, 47, and 51, and I'm transforming everyone's score into z-scores. So this first person I've highlighted in yellow with their score of 39. First I subtract the average, 45, but then I divide their score by the standard deviation. And notice again that I'm showing each and every single step. So now the person whose score that used to be 39, now they have a z-score of 1.5. Because over here, see, this is the equation over here for calculating a z-score. Take everyone's score x, subtract average, divide by the standard deviation. And I've used these symbols because this is a population. And the equation would be the same if this was a sample. The symbols would just be a little different, right? Because instead of mu, we would have x bar for the average, and instead of sigma, we would have s sub x for the standard deviation. But either way, this is in fact a population, so properly these are the symbols, right? And so 39 is transformed into a negative 1.5. 51 is transformed into a positive 1.5. 45 is transformed into a 0, right? And so now I have a set of 5 z-scores that can be interpreted. I know, let's say the person with the original score of 39 is named, Aiden. He had a z-score of negative 1.5. So Aiden is 1.5 standard deviations below average. And that's how you interpret a z-score. Let's say this is Claudia. She had a raw score of 51. Well, now she has a z-score of 1.5. She is 1.5 standard deviations above the average. And so now these are standardized scores. I maybe couldn't interpret someone's score before. 51, is that good? I don't know. But now this person tells me they're 1.5. They have a z-score of 1.5. I go, this person is 1.5 standard deviations above average. But then I ask you to find out the new average and the new standard deviation for these set of z-scores. And you may be asking yourself, hey, wait, I thought Dr. Jenny said that z-scores would always have an average of 0 and a standard deviation of 1. And that's true. But what I want you to do is demonstrate that for yourself by taking these z-scores, of which there are 5 brand new transformed z-scores, negative 1.5, negative 0.5, 0, positive 0.5, and positive 1.5, and I want you to calculate the average for them. So I go, okay, let's add these all up, to get 0, divide by 5 to get the average of 0, right? What do you know? Those new z-scores have an average of 0, just like I said they would. And then, but now I need to calculate the standard deviation. So let's write that equation again, reminding myself that this is a population. Take each score, subtract the average, because remember, this is just mu. Square, then add them up, and divide by n. Then as a last step, take the square root, right? Right. So here is me. So here is me taking the z-scores, see, negative 0.5, a negative 1.5, negative 0.50, subtracting the average of 0, because that's the average of z-scores, to get negative 1.5, negative 0.5. But notice I'm showing you that tedious step. And so these are my deviation scores. And so then you're going to get, then I'm going to square those deviation scores to get 2.25, 0.25, 0, 2.25, 2.25. Then I'm going to sum those to get the sum of squares, 5. Then I divide by 5. Oh, hey, the variance is 1. Take the square root of the variance to get the standard deviation of 1, just like I said it would be. So the average of these z-scores is 0, and the standard deviation of these z-scores is 1, just like I said it would be. But you got to show all that work in the problem in the lab. And now we get to question 3, which puts it all together and requires you to use the standard normal table in the back of your book to answer some interesting questions about the probabilities of being between or above or below different scores on a normally distributed variable. So let's read the problem. A couple's researcher is measuring how satisfied people are with their relationships on a scale of 1 to 8. She gathers data from 144 people, and her participant satisfaction ratings are normally distributed. Ah, that's important. I'm telling you that her participants' satisfaction is in fact distributed, right? I'm telling you that the satisfaction ratings are normally distributed. And so the average satisfaction is 5.5 points. Ooh, I have seconds there. That's a typo. Sorry. We're just going to have to bear with it. It should say points. The average satisfaction rating is 5.5 points with a standard deviation of 0.5 points, right? So I've asked 144 people how satisfied they are with their relationships. The average is 5.5 points and a standard deviation of 0.5 points. So the average X bar is 5.5 with a standard deviation of 0.5. So I'm just telling you that. You don't even have to calculate it. But I'm then also telling you that these ratings are normally distributed, that they're in fact normally distributed. So now you are going to need to use table A1 in the back of your book, which is called the standard normal table. And I will teach you how to interpret this table. But keep in mind, for all of the following questions, you're going to have to start by turning things into z-scores, because the table in the back of your book requires you to standardize the scores first. Because there's not a table for every single variable out there in the world. The table needs you to standardize the scores first, turn them into z-scores. So, what proportion of the people? Well, what proportion of her participants will be between a score of 5.25 and 5.75? So those are the raw scores, right? And our first step in order to be able to use the standard normal table is to confirm that it's normally distributed. Is satisfaction normally distributed? Well, I told you that it was. But now our next step is going to convert these scores into z-scores, so that's exactly what I do. I take the raw score of 5.25, subtract the average of 5.5, and then I divide by 0.5 because that's the standard deviation. So I told you it was. And remember, this is our equation for turning something into a z-score, right? So first I've subtracted the average of 5.5, then I've divided by the standard deviation. So the first person who had a raw score of 5.25 now has a z-score of negative 0.5. Here they are. The second person that had a raw score of 5.75 has a z-score of positive 0.5. They're half a standard deviation above the average. And so now here's how you use table A1. And so I'm just taking a pause from the problem now just to teach you how to use table A1. And here is a little screen capture from table A1 right here. So essentially, table A1 is called the standard normal table. And over here in the far left-hand side, it's got a bunch of z-scores. See that? 0.6, 0.61, 0.62, 0.63. These are people's raw scores that have been turned into z-scores, or any number that has been standardized and turned into a z. And so as long as whatever it is, whatever thing you're looking at is normally distributed, whatever group of numbers you can feel confident is normally distributed, this table can tell you two things. It can say, okay, from that z of 0.60, right, from the z-score of 0.60, right, this first column tells you the percentage of people that will be between that z-score and the average of 0. Because remember, let's look at this picture here, right? See how it's got a little bell-shaped curve? That's because this table only works if you know ahead of time that this variable is normally distributed. It's got a bell-shaped curve. And so it's got a bell-shaped curve, and here's the center, and the average of a bunch of z-scores is always 0. We just demonstrated that, right? So this first column here says, okay, from the z-score of 0.6, 0.6 would be like here, right? To the average of 0, 22.57% of the people will be from a z-score of 0.6 to the average of 0. I can turn that into a proportion by moving the decimal place over 2 times. 1, 2. And so now I can say that between the average of 0 and a z-score of 0.6, the proportion of people will be 0.2257. 22.57% of the people will be right in there. Or there will be a probability of 0.2257 of someone having a score between 0 and the z-score 0.6. Because remember, probabilities are proportions. So once I turn that percentage of 22.57 into a proportion of 0.2257, I can say with confidence that there is the probability of someone having a score between 0 and the z-score of 0.6 is 0.2257. And that is what the mean to z tells you. Similarly, if we look at the z-score here of 0.63, I know that 23.57% of the people will be between the average of 0 and 0.63. So there will be a probability of 0.2357, just move the decimal place over 2 times, of being between the average of 0 and the z-score of 0.63. This last column here is called the percent in tail, the percent in tail column. And so if I go back to my z-score of 0.60, I see that 27.43% of all the people will be from the z-score of 0.6, so let's say that's here, from the z-score of 0.6 and above, so in the tail, right? So from that z-score and above, that will be 27.43% of the people. Turn that into a proportion. I get 0.2743. So because proportions are probabilities, I can say there's a probability of 0.2743 that someone is going to have a z-score above 0.6. Z-score is 0.6. There's a 27.43% chance or a probability of 0.2743 that someone's going to have a z-score above 0.6. And notice that if I add 0.2257 and 0.2743, that's going to have a probability of 0.53, because essentially what this is doing is this. It's saying, okay, the average is at 0, the z-score 0.6 or whatever the z-score is, from the average to that z-score is 22.57, and then from 0.6 and the rest of it is 27.43. So that's going to be 1/2 of the graph. From the average to the z-score, and then from that z-score and above, that will be half the graph, because remember, normal distributions are symmetric, which brings me to something else that's important. These proportions that we just learned for a z-score of positive 0.6 would also be true for a z-score of negative 0.6. It would just be the other side. Instead of it being from the average of 0 to the positive score of 0.6, it would be from the average of 0 this way. To the negative 0.6, because the negative z-score is going to be below the average. And so maybe negative 0.6 is here. And so this column would tell you from the average of 0 in here. And that would still be 22.57%, or a proportion of 0.2257. So anything that's true for the positive z-score is also true for the negative z-score, right? And so the percent entailed tells me the same thing, except this will tell me, just as this told me for a positive z-score of 0.6, 27.43% of the people would be above 0.6. This would tell me that 27.43% of the people would be below a z-score of negative 0.6. And so there are no negative scores on the z-table, because what's ever true for the positive z-score is also going to be true for the negative z-score, except in the opposite direction. It's just going to flip it and be looking in the negative direction. And here is just a snapshot of the standard normal table. And I just want to put, and so let's go back to our previous problem. Here I had calculated the z's of negative 0.5 and positive 0.5, right? And so I can use this table to find the z of 0.5, which I've boxed in red there for you. And so for a z-score of 0.5, the mean to z is 19.15%. So around 19% of all the people will be between the average of 0 and the standard and the z-score of 0.5, like right here. From the average of 0 to the z-score of 0.5 will be 19% of the folks. Turn that into a proportion, I get 0.1915. So there is a proportion of 0.1915 of the folks between the average of 0 and the z-score of positive 0.5, right? So from here, and here I've drawn a little picture for you, right? Here's the average. Here's the average. Let me use a darker highlighter. Here is the average of 0. Here is positive 0.5 over here. In here is a proportion of 0.1915. So it is true to say that the probability of being between the average of 0 and the z-score of 0.5 is 0.1915, because that's the proportion of this graph. And because it is a symmetric graph, from the average of 0 to negative 0.5 is also going to be 0.1915. And so I just add those two probabilities together. And that is the probability of being between positive 0.5 and negative 0.5, because I just turned those raw scores into z-scores. And because I know that this satisfaction is normally distributed, I can figure out the proportion of people in between these two z-scores by using this graph. And I'm going to give a strong recommendation that, let me remind you of what the standard normal distribution looks like. The standard normal distribution is bell-shaped. Right? You've turned things into z-scores, and so the average is going to be 0. And then 1 standard deviation away is going to be here and be 1. 2 standard deviations away is going to be here and be 2. 3 standard deviations away is going to be here and be 3. 1 standard deviation over here, negative 1. 2 standard deviations over here, negative 2. 3 standard deviations over here, negative 3, right? And so in this, And so on using the standard normal chart, it can be really helpful that once you've turned things into z-scores, simply draw this picture and go, okay, positive 0.5 would be here, negative 0.5 would be here, and the problem asks me the probability of being between them, and then you can visualize who I'm asking about. It can make things really easy, or at least easier. Not really easy, but easier. And so now the answer then for this problem is 0.383. About 38% of the people would be between a z-score of 0.5 and a z-score of negative 0.5. And so to go back to the original question, what proportion of our participants will be between 5.25 and 5.75? All we did was convert these scores into z-scores of negative 0.5, positive 0.5, and then use this table to figure out the proportion for both those z-scores. And then you added them together. But then I ask a slightly more difficult question. What proportion of our participants will be between 4.75 and 6.75? And my first step is going to be, again, to be turning these into z-scores, right? So I turn them into z-scores. I take 4.75, or I take 4.75, subtract the x, and I subtract the average, and then divide by the standard deviation. 4.75 minus 5.5 is negative 0.75. Divided by 0.5 to get negative 1.5. Then I do that for the second score. 6.75 minus 5.5, because again, how do you get a z-score? Right, that's the z-score. So I get 6.75 minus 5.5 to get 1.25, divide by 0.5 to get 2.5. So now I've got my two z-scores. And let's just draw that picture like I recommend. The average of a bunch of z-scores is 0. Negative 1.5 would be somewhere here. Positive 2.5 would be somewhere here. And I ask about who's in here. And I know that the standard normal table can tell me the mean to z from the average of 0, from the average of 0 to the z-score of 2.5. The mean to z can tell me who's in here. And then the mean to z can tell me from the average to 1.5 who's in here. And then you just add them together. So you get the mean to z for 1.5 is 43.32. The mean to z for 2.5 is 49.38. Convert those to proportions, add them together, and then you get the proportion of people between a raw score of 4.75 and a raw score of 6.75 is 0.927, because the proportion of people between the z-scores of negative 1.5 and positive 2.5 is 0.927. If you look at the graph, yeah, that looks like about 92% of the graph, right? Because you figured out who was in here, and then you figured out who was in here, and then you just added them together to get, right, to get your final score. But then I ask you a more difficult question. I say, what proportion of our participants will be between 3.75 and 5.0? My first step is to turn them into z-scores, which I do. 3.75 minus 5.5 to get negative 1.75. Then I divide that by 0.5 to get negative 3.5. Again, showing each and every single mathematical step. Then I take for the second person, 5.0 minus 5.5 divided by 0.5. So I get negative 0.5 divided by 0.5 because I'm showing each and every single mathematical step to get a z-score of negative 1. And so let's draw that picture on a normal distribution. Where would that be? Z-scores always have an average of 0. And I got z-scores of -1 and -3.5. Well, -1 would be over here. And -3.5 would be over here. And I want to know who's in here, right? So then I use my mean to z to find out that 49.98% of the people will be between the average of 0 to 3.5. So from the average of 0 all the way to 3.5, everybody in here is 49.98%. Everybody in here is 49. .98%. About half the graph is from the z-score of 0 to the z-score of -3.5. Everybody in here. But is this what we want to know about? No. We only want to know about the little green area, not the giant purple area. So then I go back to my graph and I go, okay. The z-table also tells me that from the average of 0 to the z-score of -1 is going to be 34.13. So in just the area I'm highlighting in yellow, that's going to be 34.13%. Okay, so this whole area here is almost half the graph, 49.98. And then from here to just this yellow area is 34.13. But I want to know the green area. So think of it like pi, like not like 3.1416, but like this is pizza, right? And I want to know about this green area of pizza. How much is here? The graph just told me that this entire purple area would be 49.98%, and the yellow area would be 34.13%, but I just want to know about this green area. So I'm going to subtract. I'm going to subtract out the yellow area from the purple area, which will leave me with the green area left over, which is who I want to know about. And so that's exactly what I do here. I'm going to subtract 49.98 minus, and so because first I turn the percentages into proportions. I take 0.4998, subtract 0.3413 to get 0.1585. And so that is the probability of being in that green area here. That is the proportion of cases between a z-score of -1 and a z-score of -3.5. And an easy way to remember it is if you calculate the z-scores, if the question asks what proportion or what's the probability of being between two z-scores, between two, and you calculate the z-scores and one is positive and one is negative, you know you're going to add the mean to z's. But if you calculate the z-scores and they're the same sign, both positive or both negative, you know you're going to subtract the mean to z's to get the correct proportion of probability, which is exactly what I've done here. Now, the last part of question 3 is where we're going to use that percent entail. And here's what the question says. What proportion of our participants will report relationship satisfaction of 6.5 or greater? And I know the first thing I'm going to need to do is turn this into a z-score. So I take 6.5 and I subtract 5.5. And then I divide by 0.5 to get 1 over 0.5. So the z-score is 2. So let's draw that on the graph. Here's the average of 0. And I calculated a z-score of 2. which would be here, right? But this question as asking what percent or what proportion of the participants will be above the score of 6.5, which I've transformed into 2, and so that is here. What proportion is above 2? And so that is what that percent in tail could tell you. So using table A1 again, I look at the percent in tail for a z of 2, and I find out it's 2.28%. Not exactly 2.5, but 2.28%. Convert that to a proportion. So the proportion of people above 6.5, which has now been converted into 2, is 0.028. So about 2% of the people are going to be above 6.5, right? And so that's the answer. The proportion of 0.0228. Or the probability of 0.0228. Because remember, probabilities are proportions and vice versa. But then the last thing I ask is how many participants would this be where I round to a whole number? You know, the proportion is going to be 0.0228. But now, of the original 144 people, how many people would that be? And so then I can just multiply. If I want to know how many people that would be, I know the proportion of people would be 0.0228. So I take 144, the number in my original data set, and I multiply to get 3.2832. And I tell you you're allowed to round to a whole number, so that would be 3 people. And so that is how to do 95% of the Lab 2. Now, for those of you who've already watched the sampling distribution and central limit theorem video, for you, I will the very last question is what would the standard error of the mean be for the sampling distribution from which this sample of reaction times was drawn? Now we remember that standard error is calculated as sigma over the square root of n. And I'm telling you that you can assume that the sample standard deviation is the same as the population standard deviation. And we know that the standard deviation is 0.5. And we know that our total sample size is n. And so I take 0.5 divided by the square root of 144, right? And so then we get a standard error of 0.0416, or if I can round that to 0.04, right? Now, if you haven't watched the sampling distribution and central limit theorem lecture yet, that won't make a whole lot of sense, but it will once you do. And that's your lab assignment number 2, and which will be an excellent prediction, prophecy of what the calculation portion of exam 2 is going to look like. And again, if you have any questions, please post in the Q&A forum or reach out to me by email or come see me in office hours. See you next time.